Second Newton's law of motion practice problems. I am solving 11 and also 12 in the same video. So 11 says, what force must a rope exert to hold up a 8 kilos box? So to illustrate this, we are going to represent the box by this drawing here. And this is the rope, and because these boxes in equilibrium or at rest is not moving, so we have our weight straight down, and we have the force applied on this cable. We are gonna call FT, or a tension force related to tension. I usually label FT any force that is applying ropes, string, or cables. So now we have this box at rest. The box mass is 8 kilos. And this is a very quick and simple data table. Mass is 8 kilos, is looking for the tension on this rope. And we have the acceleration of gravity. We need this value to calculate FG. 9.8 meters per second square. So because this object is in equilibrium, so we can state that all forces up is equal forces down. In this case, I just have 2. So there will be FT is equal FG. My FG is mg, and my m is 8 kilos, and g is 9.8. So easily I can find the tension on this cable. Now let's go to the second problem. So the second problem, number 12, states, is asking, what is the force must a rope exert to accelerate a 8 kilos box upward at 4 meters per second square? Now is a very similar story, but we have a different type of scenario here. So here what we have is this box, same way that we had before, but this time we are going to accelerate upward. Does not have to be like this, but I add like a pulley system to pull this way. It could be up, could be to the right. I just choose to do this way. There is no, what is happening here is not going to affect in our analysis. But I'm gonna read, and I'm going to fill the data table. So the mass of the box is 8 kilos, is looking for the tension on this cable, is giving the acceleration, so is moving upward, is changing velocity over time upward, which is the acceleration is 4 meters per second square, and the acceleration of gravity is 9.8 meters per second square. Now there is a big difference here. The acceleration of gravity is a established number. This is never going to change on Earth. It's 9.8 meters per second square. Now this acceleration here is a controlled acceleration. Is acceleration that is due to the shift of velocity. So that's two things very different, even though both are acceleration. Okay, so to solve this problem, we are going to use Newton's second law, and but before that, we need to establish our reference. So for this case, when we have a situation like this, if it's moving upward, it's accelerating upward, so your upward or up is going to be your positive reference. And you need to establish that before you do anything. So now our F net, why F net now? Is because you have more forces involved in the same direction. When we have forces like, for example, the wheelbarrow example practice problem, we have a pushing force and we have the weight, but they have two different directions. Now we have those two forces acting the same, even though one is up, one is down, but they are the same vertical direction. So my F net is equal to my force on this rope, the tension force, because it's positive, because that's what is making this accelerate upward, minus, because Fg is the opposite direction of the motion. Now I have minus Fg. Okay, so now what we are going to do is we are going to replace everything. F net is ma, Newton's law, and the Ft is what I'm looking for, and Fg is mg. So the mass in this problem is 8 kilos, and the acceleration is 4 meters per second square. Ft minus 8 is the mass again, times the acceleration of gravity. This is the weight. And then this is just like basic math. We can like the product of these is 78.4, and because it's negative, we are going to add on both sides 78.4 plus 78.4. We can eliminate those two. Now we have Ft is equal 78.4 plus 32. So my Ft is 110. So I'm trying to fit both problems together side by side so you see the difference. So this is at rest and this is in motion. So we have to establish the reference. The reference goes with the motion. If the reference is, the motion is up, so we're gonna call this positive. And then we need to look the directions of the forces because they're arrows, they're vectors. And then we are going to set up this equation and solve this problem.